Answer. Let me give it. If you got this, you're good. If you didn't get this, we gotta fix it. 3x cubed minus 28x squared plus 49x plus 46. Okay. You got it right, Luke?
Yeah.
All right. So you got 3x cubed minus. Oh, you're right. You're just clear almost. Minus 28x squared plus 49x plus 46. All right. So yes, you do need to know how to do this. Now, the directions will be specific. It'll say, make sure you have integer coefficients, no fractions, and you're going to want to multiply everything out. Like I said, let me go through this here. All right, negative 2/3. Okay. You can do x plus 2/3, but that's going to give us fractions. So we've talked about this earlier. If negative 2/3 is an answer, what's actually going to be the factor? We don't want to use x plus 2/3, but we want to use what?
3x plus 2.
3x plus 2. So we want to use 3x plus 2. And now I got x minus 5 minus square root of 2. You always subtract whatever your root is. And then I got x minus 5 plus square root of 2. We talked about they always come in pairs. So if you got one, you got to have the other. Doing these, I'm not gonna try to do 3x plus 2 times this one. Work with those two with the radicals first. And when I rearrange, I can make this x minus 5 plus square root of 2. And then I make this x minus 5 minus square root of 2. Okay. And then when you FOIL, we've talked about this, I've talked about it. This becomes x minus 5 quantity squared minus 2. Well, this is all one little piece. You got to simplify that all the way down. So you got to FOIL that and then subtract 2, and then take that answer times the 3x plus 2. So that's going to be x squared minus 10x plus 25 minus 2. And then those combine to give me x squared minus 10x plus 23. All right, so at this point, you get 3x plus 2 times x squared minus 10x plus 23. I do want you, I'm not going to go through the multiplication of this. You guys can do that. But I do want you to multiply it out. I'm not going to write the whole thing out. But when you are done from here, this is where you, and sometimes it's okay to leave it like that, but this time I don't want you to. This is, when we're done, we'll get 3x cubed minus 28x squared plus 49x, okay, plus 46. Okay, so that'll be the case. All right, do need to know how to do that. We're looking at tests. It's a 2-day test. It's a no calculator part one day, calculator part the next day. So we're looking at next Tuesday and Wednesday. I believe it's the second and third. Yes, it is. When we go through those. All right, so that's our final answer. Also similar to 21 from the homework. Now on the homework, 38 was the only one that wasn't in the back. Use the graph to get your roots. Okay, use the graph to get your roots. And it bounces at 1. Okay, it bounces at 1. So that means you have to use 1 in the synthetic division twice. All right. Austin, do you have the original equation for 38?
Yes.
What is that?
X to the fifth minus 2x to the fourth minus x to the third plus 8x squared minus 10x plus 4.
Okay, so this case here, looking at the graph, so it's x to the fifth. It's got to hit at -2, and it's got to hit at 1. And I'm not sure of all the particulars, but it's got to have some type of shape like that. So since it hits at -2, We plug that in. And I get 1, -2. That's a -1, 8, -10, and 4, 0, 1. Let's see, -4, 8, 7, -14, -6, 12, 2, -4, 0. And then I use 1 here. That's -3, 4, 4, -2, -2. I get another 0. And you got to use 1 again because of the bounce. And then so this is what we end up with is the x squared minus 2x plus 2. And then we got to set that equal to 0. And then that's where you use your quadratic formula. And what did we get for our other two answers? We got 1 plus I and 1 minus I. Okay. So on these complex and on some of the problems, I'll allow you to use your calculator. There'll be some cases where you have to do pure guess, the rational zeros theorem and just test. This case here, with complex answers, I'm going to let you go ahead and solve that. For 21, okay, here is the case that they give you. I think they just said 5 minus I and 3I, but that indicates that the conjugate is also a root. Leading coefficient is 0 or 2. So this is a little bit of what it's going to look like. You got to work with these two together. You got to work with those two together. And so so you get x minus 5 plus I, x minus 5 minus I there. And when you multiply that all out, you should end up with x squared minus 10x plus 26. That is this piece here. That becomes this. And then x minus 3i times x plus 3i becomes x squared plus 9. And then you multiply those two together, and in the end, you distribute that 2. Okay, so there's a lot going on there, but that's kind of how you end up with that final answer. Okay, so I just wanted to at least cover that a little bit. All right, anything else I can go over? Okay, we do have one more section that we're going to cover that's going to be on the test. So there's a lot in this section, section 3.6. I do have some guided notes for you. You got them. All right, one of the big things, well, we're going to define it first, rational function. Well, from our numbers, what does rational mean with a number? What should you think about? Okay, a rational number as opposed to an integer. What's the difference between a rational number and an integer? Oh, wrong. Okay. Oh,
An integer is only whole numbers. Rational numbers is anything that's not like a non-real number, like infinite decimal.
That's irrational. That's irrational. Integers are only whole numbers. Agreed. But rational numbers include terminating decimals, so it doesn't have to, and then repeating decimals, which always can be converted to a fraction. Rational numbers, kind of think fraction. Okay? So a rational function is going to be a fraction. We're going to talk about vertical asymptotes, horizontal asymptotes. Vertical, you're really comfortable with because you had them a lot. Horizontal, not anywhere near as comfortable with. All right, this is not on your guided notes. Actually, we're going to skip this one. We're going to get to it later. So this is an example of a rational function. This is something that we're going to get to. You should know, what is the vertical asymptote of that? 3. It's where it doesn't exist. Okay, 3. All right, so we'll get to that a little bit later. All right, here's your definition. And this is what goes in that little space there, what's highlighted. A function f that can be expressed in the form n of x divided by d of x. Well, n, if you figure that out, kind of stands for numerator. D kind of stands for denominator. Yeah, tricky. Where the numerator n of x and the denominator d of x are polynomials. They got to have at least an x in them. Okay? And d of x is not the zero polynomial. It's called a rational function. The domain of f consists of the real numbers for which d of x doesn't equal 0. Well, it goes back to you can never divide by 0. So that's still in play. Still in play. All right, here's your definition of vertical asymptotes. Okay? The line with the equation x equals a is called a vertical asymptote of the graph if, okay, now they just throw the absolute value. As f of x goes to infinity, as x goes to a with a little plus or a with a little minus. That means from the right or from the left. I like to put the x first. So you can, you might see it as this, as x goes to a from the right, f of x can go to infinity. Or as x goes to a from the left, f of x can go to negative infinity. And I'll explain what this right and left means here in the next slide. All right, here's kind of all your definition. All right, you see as x goes to a with a negative, here's a. It means using numbers less than a, which would be on the left. So if you think of this as 2, we're starting with 1, and then we're going to 1.5, 1.6. So we're getting closer this direction. Well, what's happening as we get close to that a, that's going to negative infinity. As we go from the right with a plus, okay, it's obviously on the opposite sides, it's going different directions, so it goes to positive infinity. As x goes to negative infinity here, or as x goes to a on the left, it goes up to positive infinity. As it goes to a on the right, it goes to negative infinity. It will not always go opposite directions. Sometimes the vertical asymptote will go the same direction. So in this case here, as we approach a from the left, it goes to positive infinity. As we approach a on the right, numbers bigger than a, it goes to positive infinity as well. And then down here, they both go to negative infinity. So there's a lot going to happen with the vertical asymptotes. All right, it says find the domain of each rational function. List any vertical asymptotes. So they kind of go hand in hand. Domain and vertical asymptotes. Words not defined. Well, where's the one place it doesn't equal 0 at? Or excuse me, it equals 0 at. It is 1. So our domain, and we're always going to list that in a notation, is negative infinity to 1 union 1 to infinity, not including 1. Right, the only thing you got to be careful with vertical asymptote is you have to label it correctly. It's an equation. It always starts with an x. So our vertical asymptote okay, your vertical asymptote is x equals 1. So they go hand in hand. Whatever your domain doesn't exist, you're going to get a vertical asymptote. Okay. Now you would have to test it to determine whether it's going to positive or negative infinity. But right now we're just identifying. Okay, now we have an x in the numerator, we have an x in the denominator. It's a rational function. G of x. Okay, copy that down. X over x squared minus 6x plus 8. So in order to figure out where it equals 0, what do we got to do to the denominator? We got to factor. So it's going to be x over. That's going to factor into x minus 4 times x minus 2. So x cannot equal 4 or 2. So domain, okay, negative infinity. That first one I come to is going to be 2. Union, 2 to 4, union, 4 to infinity. Okay, vertical asymptotes, I'm just going to abbreviate it VA. X equals 2 and x equals 4. We're going to have more than one vertical asymptote, okay, which is fine. All right, once you think about it, copy that down. All right, think about that. Okay. We want the denominator, we want to see where the denominator equals 0. Where is that going to equal 0? It is not. You cannot factor that. Okay, it's x squared plus 4. If it was x squared minus 4, then you could factor in x minus 2, x plus 2. This does not factor. Okay? Think about it. No matter what number you plug in for x, it's going to come back positive, and when you add a number to it, it's going to stay positive. It's never going to equal 0. So our domain is all real numbers. There is no vertical asymptote. Okay? So our domain, negative infinity to infinity, and there is no vertical asymptote. It does not matter where the numerator equals 0. That makes no effect on the vertical asymptote. All right, now D. Okay. Find the, again, same directions. Find the domain and vertical asymptotes. Now in D, the numerator does factor. Go ahead and factor that. And now that is a difference of squares. So that factors into x minus 3, x plus 3 over x minus 3. All right, those will cancel. So you are left with f of x equals x plus 3. Now our domain, so this is what the graph's going to look like. X plus 3 is what type of graph? Linear, straight line. So it's going to be a straight line. But you got to take a look. Can I plug 3 into the original function? Because what happens? I get 3 minus 3, which is 0. So you still have to throw out 3 from the domain. So the domain is going to be negative infinity to 3 union 3 to infinity. But here's what you got to watch. There is no vertical asymptote. This is what that graph will look like. This is a case. It breaks down to a line with a hole at that point. That is not a vertical asymptote. A vertical asymptote must, let me go back here. Okay, if you got a vertical asymptote, it must go towards infinity or negative infinity around that value. This one doesn't do that. It's just undefined there. Because when we divide, we're left with x plus 3. So there is no vertical asymptote. Now, if you got a little bit of room, it wouldn't hurt to put that down, that graph, just so that you make that connection between that equation and what it's going to look like. Okay, it is not a vertical asymptote. It is undefined at that point. Got a hole in the graph. Okay, but it will not be considered a vertical asymptote because it doesn't go to positive infinity or negative infinity around that point. Okay. And that happens here in the original function when that cancels, the denominator cancels with something in the numerator. All right, flip that over once you're done there. Let's talk about horizontal asymptotes. Okay. Similar concept. Okay, the line with the equation, now we call these y equals a constant. It's called a horizontal asymptote of the graph of a function if, as x goes to infinity or x goes to negative infinity, f of x goes to a constant. Now I'm going to go back here for a second. I'm going to go backwards. I'm going to go to this. Okay. And I'm just going to graph it even though you don't have a whole idea. You get a vertical asymptote at 3. Even though you don't know why, I'm going to tell you now, we're going to get a horizontal asymptote at 2. What do I get when I plug in 0? Just mentally plug that in. What do I end up with? Negative 1/3, right? So let's see here. No, it actually would be positive 1/3, right? So it's going to be positive 1/3. So 0, 1/3. Here's what this graph's going to look like. And we'll eventually get there. Vertical asymptote, it goes to negative infinity or positive infinity. Here, a horizontal asymptote means as you plug in bigger and bigger numbers, it gets closer to that value. So plug in, if you let x equal 100. Okay, we can do this. Isn't that hard? What's 2 times 100? It's 200 minus 1 is what? 199? What's 100 minus 3? It is 97. Real quick, just do that on your calculator for me. Amusement. What's 199 divided by 97? Round it off to the nearest hundredth is good enough. Luke Candle, let me know what you get. 2.05. 2.05. All right, let x equal 1,000. Okay, 2 times 1,000 is 2,000. Minus 1 is 1,999. 1,000 minus 3 is 997. All right, what's 1,999 divided by 997? Casey, let me know what you get.
2.01.
2.01. Okay, so now let's make a jump. Put in a million, which in math is really, not that big, but we think it's huge. So a million minus 2 times a million is 2 million minus 1. Holy cow, 1,999,999 over a million minus 3, 999,997. So that's going to be a few zeros, I imagine. Let me see what it looks like. Oh, how many zeros we got before we get that 5? 1, 2, 3, 4, 5 zeros, right? All right. Will it ever go below 2? It's never going to go below 2. You can plug in 10 million, 100 million. It's going to get close to 2. Okay, that's what's happening. That's a horizontal asymptote. Got it? So as I plug in bigger, if I plug in negative numbers, it's going to just be below 2. It's like going to be 1.99999. All right, that's how horizontal asymptotes work. Now, this is huge. This is huge right here. A graph will never touch or cross a vertical asymptote. A graph can cross a horizontal asymptote. It is not undefined there. It is just saying as we plug in big numbers, our answer is getting close to, in that case, 2. It's getting close to a constant. When I'm plugging numbers in or close to 0, anything can happen. All right, so that's going to be real important. Unlike vertical asymptotes, a graph can cross a horizontal asymptote. That's going to be your biggest thing because you're never going to want to do that. All right, finding is a little bit different. Okay, find the horizontal asymptote of the graph of each rational function. All right, I just want you to look at that. Can you think about what the horizontal asymptote would be? So do you understand the concept? Okay. What would be the horizontal asymptote of 1 over x? As you plug in really big numbers, what does that get close to? What was that? 0. Because what's 1 over 1,000, 1 over 10,000, 1 over a million? It's going to get close to 0. It's going to be 0.000 something. What about 1 over the negative? It's just going to be negative. So our horizontal asymptote is y equals 0. Okay? That would be the case. Now that one is not too hard to kind of mentally check. I'm going to give you a little procedure here. Okay. All right, your equation. Find the highest degree individual term, which is just going to be first degree, right? We're going to divide everything by that x. So take your equation, okay, and I'm going to rewrite this as f of x equals, and as long as I do the same thing to everything, I'm okay. I'm going to divide everything by x. Okay. Okay. Then, as long as I do everything the same thing, it keeps it equivalent. All right. Simplify it. What is 3x divided by x equal? That equals 3, right? X divided by x. Be careful. That just equals 1. Plus 7 over x. Can't do anything with here. All right. Now here's what you want to do. Let x get really big and really small, but you really only got to analyze in one direction. Let x go to infinity. How does it affect each individual piece? Well, you've got a 3. It doesn't affect that. You got a 1. What does 7 over infinity get close to? 0. It doesn't matter what number you have over infinity. It's always going to get close to 0. So this key right here is going to equal 0. What does that mess then boil down to? It's just 3 over 1 plus 0, which is what? 3 over 1? So this whole thing, as x goes to infinity, is going to get close to 3. That's your horizontal asymptote. As I plug in really big numbers, that's going to get close to 0. I'm going to be left with 3 over 1. Okay, g of x, 7x squared minus 4 over 2x squared plus 9x. Find the highest degree piece, second degree. Divide everything by that. Okay, divide each little term by that. So we get 7x squared over x squared minus 4 over x squared. 2x squared over x squared plus 9x over x squared. Simplify. 7x squared over x squared is 7 minus 4 over x squared. Well, you can't do anything with that, so just leave it. 2x squared over x squared is 2 plus, this will simplify to 9 over x. Okay, let x go to infinity. So plug in really big numbers. If you got a constant, it's not going to affect it. But what's 4 over infinity squared going to go to? Or get close to? It's going to essentially be what? Still got to be 0. So basically this is going to be equivalent to 0. What's 9 over really big number going to get close to? 0. So what am I left with? 7 over 2. So my horizontal asymptote is y equals 7/2, which is 3.5. So you plug in big numbers, it's going to get close to 3.5. All right, let's take a look at one more. H of x is 2x plus 5 over 3x squared. Highest degree, x squared. 2x over x squared plus 5 over x squared divided by 3x squared over x squared. Simplify everything. Well, 2x over x squared just becomes 2 over x. This is 5 over x squared. I can't do anything with this. And then 3x squared over x squared just becomes 3. Okay? Let x go to infinity. Let x get very big. 2 over a very big number is basically what? 0. 5 over a very big number squared. Well, like if you square, it just makes it even bigger. So that's actually going to go where as well? It's going to go to 0. All right, what am I left with? What's that going to be? On top, you really are just left with 0 over 3, which is what? 0. So my horizontal asymptote. Horizontal asymptote. Y equals 0. All right, horizontal asymptote is a little different. You're much more familiar and comfortable with vertical asymptotes. So really pay attention when you're doing some of these problems. Some of these are just matching it. It's nowhere near as many problems as it looks like. I mean, it's not that much work is what I'm trying to say.